when adding, subtracting, or considering scale multiplication of a vector, we can consider graphical interpretations. So for vector addition, an easy way to envision adding two vectors together is by attaching the two vectors from head to tail. What does that mean? So suppose you have two vectors, u and v. Let's say vector u looks like this. And over here, we're considering vector v to look like that. So I'm going to take a copy of vector u here and place it at the origin. And I'm going to take a copy of vector v and instead of placing it also at the origin, I'm going to place it at the head of vector u. The vector that I get from if I started at the tail of vector u and ended at the head of vector v, that is going to be the sum of u plus v. So whenever adding two vectors together, you can get a quick visual interpretation of the sum of the two vectors by going through this geometry. Here's another example of this. Let's say we're talking forces. And you have an object right at the center at the origin, 0, 0. And this object is being pulled in this direction by a certain force. And in this direction by another force. We can call the red force U and the green force V. If you were this object being pulled in these directions and the lengths of these vectors gives you an idea of how strong those forces are, ultimately, in which direction will you be moving if these forces were enough to move you? I'm thinking that I will be moving somewhere upwards because both of these guys have components that are pulling up. And because the green vector is a lot longer, I would be probably moving a little bit towards the left-hand side. To add these two vectors together, I can use the process above. So I can, if I wanted to look at the graph of, or consider what the vector u plus v will look like, I can start by getting a copy of vector u. Starting that guy at the origin. And getting a copy of vector v. And placing the tail of the green vector at the head of our red vector there. So the sum of these two forces is going to be the vector that starts at the origin at the tail of vector u and ends at the head of vector v. So the blue vector would be u plus v. And as expected, this vector generally points upward, and this vector generally points towards the left, right? So I would be feeling a force that goes up and to the left. We can have a graphical interpretation for scalar multiplication as well. Suppose we have a vector u that points in this direction. If I were to consider 2u, this will give me the vector that will be twice as long. If I were to consider 3u, it would be the vector that's 3 times as long. If I were to consider the vector 1/2 u, it will be the vector that's 1/2 as long, right? So if you multiply by a scalar, you're pretty much just either stretching or compressing that vector. And if we multiply the vector by -1, we would get the vector but pointing in the opposite direction. So this guy would be -u. We can use our concept of vector addition and vector scalar multiplication to also think about vector subtraction graphically. So suppose that you have vector u looking like this and vector v looking like that. If you want to consider the graph of u minus v, you could think about this difference as u plus -v. So vector u, again, will be this vector looking like this. Just copy and paste it from the left-hand side. But instead of working with vector v, we're going to consider vector -v. And that will be taking this vector and going in the opposite direction. So vector -v would look somewhat like this. So if I want to add these two vectors together, I can have u there and then attach v to its head. And the resultant vector is going to start at the tail of u and end at the head of v. It just so happens that in this case, it looks like that guy's just pointing straight down, and that's okay. Another way of envisioning vector addition and vector subtraction is by using a parallelogram. Suppose that you are given two vectors u and v. So let's say u is here and V is there. So we can make copies of these vectors to create a parallelogram. So if I were to make a copy of vector u and place it up here, so that's a copy of vector u, and I'll make a copy of vector v and place it over here. That's a copy of vector v. Notice that here we have u and v attached together from head to tail. So from our discussion above, the vector going from here to here is going to be u plus v. So in the parallelogram, this long diagonal is the sum of the two vectors. In the same way, we can think about vector subtraction using a parallelogram. So again, suppose that you have vector u there and vector v here. We can consider making copies of vector u and a copy of vector v. Now this is vector v, but if I were to have it go in the opposite direction, then this would be vector negative v. And consider that this vector attached to this vector here is u plus negative v, because these two guys are attached from head to tail. So u plus negative v also known as u minus v is going to be the vector that starts from right here and ends right there. So u minus v is a vector on that parallelogram along the other diagonal. So whenever I'm graphing these guys and I have to graph u minus v, I know that it's going to be the not the vector along the long diagonal, but the shorter diagonal. And I have options of whether to start from here and go that way, or start from here and go that way. So to know which one of these two options to use, I'll look at the vector that has a negative. And in this case, vector v has a negative, so that's how I know where to start. I'm going to start at the head of vector v and end at the head of vector u. Now, in a lot of calculus applications, you'll be generating these parallelograms, and these parallelograms will be right in front of you. And then you'll be able to pick out the sums and differences of these vectors using this technique.